Hi, and welcome to another lecture. This time we're going to look at cycles around compact, so putting cycles around compact sets. This is subsection 6.3.3 in the book. You can get the book in the link in the description. You can either get it as a PDF for free or you can get a paperback if you want. All right, so what are we trying to do? Suppose that we have a compact subset of an open set U. We're trying to find a gamma that, so it doesn't go through K. It's supposed to go around K. But it's supposed to also be homologous to 0 in U. So it shouldn't go around anything on the outside of U, but it should go around K. All right, this is the more technical statement of what we're trying to do. So suppose that we have an open subset of the plane. K is compact and non-empty, otherwise there's nothing to do. And if we have that, then there exists a cycle gamma that doesn't go through K, but it's in U, so it's in U minus K. And the winding number around every point in K is 1 exactly, so it goes around once every point in K. And it doesn't go around any point in the complement of U, so it's homologous to 0 in U. And actually, we're going to set it up so that it doesn't go around anything more than once, or in the opposite direction, or anything like that, right? It's the winding number for every point not in gamma is either 0 or 1. All right, now there's lots of ideas of how to prove this, and that the standard idea is to put a grid over the complex plane, and then go around little squares, and putting those little squares into the sides of the squares and building the gamma out of that. But anyway you do it, there's always a bunch of nitty-gritty details that you have to check. This is really why we haven't done it yet. But what I want to do is use it as an application of how to use the Riemann mapping theorem to prove something that doesn't seem to involve anything about the Riemann mapping theorem. It might not be the most obvious way to prove this, but in a simple case, it would be, in the picture that I'm going to draw, it's almost trivial to do it. But then again, we have to check a bunch of nitty-gritty technicalities that we have to handle, because K is ugly and possibly U is ugly. So it's, there's stuff to do. So what's the idea? So suppose that we have a compact set K inside some U, right? So what we're gonna do, and we're trying to find this gamma. That's this guy over here. So some positively oriented guy that goes around K, doesn't go around anything in the outside. Now what we're going to do is we're going to take the outside of K, so everything out here, except for K, and let's assume that 0 is in K. We're going to take 0 to infinity, right? And we're going to take the outside of K, including infinity, we're going to take that to the inside of a disk. And it's not always possible, but if it was this picture, it would be possible, right? So if you take it to the inside of the disk, like over here, nicely color it in, then what you can do is you can go around. So where does the outside go, right? The outside of U goes into a compact subset of the disk now, right? So you can go around the outside of U, well, wherever the outside went, right? You can go around by, sort of tracking sufficiently close to so going around very near the boundary of your disk, because this inside is compacting your disk. So you can definitely go around some circle of radius, some R. And well, this sort of does the wrong thing if you think about it. It goes around the outside of U, but if you check what it means, because there's going to be basically 1 over z here, right? That's the inversion. That's taking infinity to 0 and 0 to infinity, wherever the infinity would be out here. So it's, if you check what that means that if we go around the other direction, the opposite direction around the outside of U, we'll be going around the positive direction around K, right? So basically, oops, wrong button. It's basically, it's very easy to do this problem if the domain was a disk, and so we want to use that, right? Except it's not so simple, because U is definitely not simply connected, right? So, all right. So how do we make it into this picture? Basically, is the idea. And then some of these things are, we're going to do it in 2 steps. That's why there's sort of 2 maps here, which is going to take the concatenation out of this, right? But there's, again, there's a bunch of tricky details to do, but not too bad. So first technicality is that K could have infinitely many components. I mean, K is just some compact set, some crazy compact set. Well, that's easy to figure out, or easy to get around. If K is compact, so it's going to be covered by little disks, and K is compact subset of U, so it's some positive distance away from the boundary of U, so we can cover it with disks of some specific radius, right? Some fixed radius. And so, because it's compact, we can actually use finitely many such disks. And we can make those disks closed by just taking a slightly smaller radius if we need. So there is some fixed number R, right? And we can cover K by this union of finitely many closed disks, right? And we're going to call it K prime. Now, K prime is compact. It's a finite union of compact things. It's compact. It's still a subset of U. That's how we picked the R. And it only has finitely many components. It's, well, it has at most M components, but probably fewer, right? I mean, M could be large, millions and millions of disks, but still finite, right? But probably a lot of them are going to overlap. So you will you'll probably get fewer than M components, right? But it's finitely many, and it contains K. And that's sufficient because if I find a gamma around K prime instead of K, well, then K is inside K prime, so therefore it's going to go around K as well. All right, so now we have K, and it has finitely many components, K1 through Kn, right? So, all right, so let's, and this is the reason why we had to first get rid of the infinitely many components. Let's split up K into 2 bits, right? K1 and the union of the rest. And we want both of those to be compact. So it's, and if we had infinitely many components, the union of everything except the first component would not be necessarily compact, right? So both of these are closed subsets. Now, if we can prove the lemma, prove the result for K1 instead of K, and instead of U, we're going to use U minus this closed set. So this is, again, an open set, just slightly smaller, right? We're taking out all these, all the rest of these components of K. And we're going to find a cycle gamma, so gamma 1. Then we're done. Well, I claimed that we're done. Why are we done? Well, repeat the procedure for each one of these components, Kj, right? So we're going to find this gamma j, and it's going to be, it's going to go around Kj, and it's going to be homologous to 0 in U minus the rest of the components, right? And then I'm going to add up these cycles, and that's going to be my gamma. All right, now, the gamma j, the way that we get it, right, is that, well, what it means, if the lemma is true for, in this setting, is that it's going to go around Kj, right? So the winding number around points of Kj is going to be 1. And because it's homologous to 0 in this bit, in and u minus the rest of the components of k, then it's not going to wind around any of the other k's, right? Any of the other, you know, I call it KL, right? So if KL or L is not equal to J, then gamma J does not wind around any point in KL, right? So that means that this sum does the right thing, right? It only winds around, whatever point in some KJ. It only winds around it once because only one of these gammas, right, the gamma J, winds around it, and all the other ones don't. Right, so this gamma works. So without loss of generality, we've just proved that we can just assume that K is connected. Right, so we went from infinitely many components to one component. Yay, right? And it's also one component that is a union of this, right? Now, assume that 0 is in K. We can do that just by translation, right? So you can definitely just assume that. And assume the K has more than 1 point. If it has 1 point, it's trivial. We just go around a little circle. So who cares? We can do that, definitely, right? So the tough part would be, well, what if it has more than 1 point? What to do then? And it's going to have more than 2 points either, right? as well, right? Because it's connected, right? So it's going to always have infinitely many points if it has more than one. But that's not an issue here. Now let phi be this inversion is 1 over z, and I mean I could have just written 1 over z, but it seems to me that it's better to give it a name if we want it to be also defined at 0 and infinity, right? So this phi it's a holomorphic self map. It's this linear fractional, right? That takes the Riemann sphere to the Riemann sphere and switches 0 and infinity, right? So that's the phi, right? It's basically 1 over z, right? Now let v, so v is going to be in this sort of upside down world, right? It's going to be the complement of k, right? So we take the complement of k in the Riemann sphere and we push it forward by phi, right? That's what v is, right? Now, v does not include infinity because, well, the complement of k does not include 0 because 0 is in k, right? Similarly, 0 is in v because infinity was not in k, right? Infinity went to 0, right? Now, v is not the entire complex plane because k has more than 1 point. And finally, the complement of v, which is really just push forward of k, that's connected because k was connected. So the components of v are simply connected. It's a little bit of an exercise, so I'll just leave that to the viewer, I think, or reader. Presumably you're reading the book. So left to student. It's not that hard, but it's not completely immediate either, right? But basically, we will get. It's basically using this thing that if the complement is connected, then the set is simply connected. So all right. So the components of V are simply connected. Now there could be multiple components, but K is a union of disks. So both K and its complement is going to be nice enough. It can have at most finitely many components, right? That's not hard to see. So V has at most finitely many components. So we're going to call them V1 through Vm, right? And those are all simply connected. So by the Riemann mapping theorem, for every j, there's a biholomorphic map from Vj to some disk. So let's make these disks of radius 1, and let's make them spread out over the C. Just let's make sure that they're disjoint, right? A bunch of disks and they're all disjoint, right? We can definitely do that. We can choose these QJs any way we want, right? So what do we have? Well, we have a domain D, which is the union of these disjoint open disks, right, of radius 1. And and there's a biholomorphic phi that takes v to d, right? Because it takes each vj to one of these disks, right? So just put it together, and we have a biholomorphic map of v to d, right? And we could assume that q1 is 0, and that phi takes 0 to q1, so we can make sorry, not phi, psi. Psi takes 0 to 0, right, which is q1. Now, the outside of u in the Riemann sphere, right, so including infinity, is compact. Right? Obviously not in C. C minus u is not going to be compact, but C infinity, the Riemann sphere minus u, well, because the Riemann sphere is compact, therefore C minus u is compact because it's closed. So therefore, the if I push forward by phi, by the 1 over z, essentially, right, this outside of u, it goes into v, right, because v is the complement of k and u contained k, right? So it's a compact set there because, well, phi is a continuous mapping, right? So it takes compacts to compacts. And we can now, so we have some compact subset of v, and we have again a continuous map. Much better, bihomorphic, but definitely continuous. So we push forward this compact set, and we get this compact set, right? And it's a compact subset of D, right? Well, let's call it S, just because that's a lot to write. Okay, so it's a compact subset of D, and D is a union of these disks of radius 1. So there exists, and finitely many disks of radius 1. So there exists some R, slightly less than 1, such that S is within a radius R of all these Q1 through Qm, right? Basically, that S is a subset of these disks, right? Slightly, we can take slightly smaller disk, and S is still inside because S is compact, right? So it's a positive distance away from the boundary of D. So this is that circle, right, going in the other direction. So we're gonna let these gamma j's be these circles. They're really gonna be minus. This is the cycle algebra minus, right? That we're reversing the orientation, reversing the direction of gamma. So well, I'm doing it in the opposite direction. It should be this direction. This is positive. This is negative, right? So it's in the negative direction around the boundary of these disks of radius r, right? And so this is an explicit statement, the explicit expression for it, right? So those are our gammas, little gammas. Okay, so now we take those gammas, and by the way, notice that where the negative, negative orientation comes in is over here, right? That minus in there, right? It's going in the negative direction then. All right. So let capital gamma J be basically, we take this little gamma J that's in, basically that's in D, and we pull it back by first C and then by phi, right? To get something that's in the original complex plane, right? We undo these changes of variables, right? So we get some, and then we just put these together, right? So we get some gamma, which is just the sum of these gamma j's, right? We had m of these little gamma j's, so we have m of these capital gamma j's, right? So now we just have to show that gamma does the right thing. All right. Well, so it's just a computation, right? So what is the winding number around P, where like P is just anything that's not in gamma, of course. So well, it's I have m m cycles, which are actually m paths, right? So these are actually explicitly given single paths, right? There's the pullback of these circles, right? So, and I just integrate 1 over z minus p. Of course, I have to get this 1 over 2 pi I, right? And I add it up, right? And these are the gamma j's, right? Okay, so I do the first change of coordinates, right? This phi 1 over z. So I'll let you work it out. That's what it is, right? I mean, after a little bit of algebra as well, right? So we have so I'm moving I had 1 over zeta here, and so like moved it over here. So I have minus 1. It's coming from taking the derivative, right? And then I have another zeta out here. So this is the expression, right? That's just the change of variables, the 1 over z change of variables. So now I'm sort of in the middle step, and I undo that change again, right? And again, I'll let you work it out. That's what it is. It's a little bit more complicated. I get this this guy in here. It's coming from the D, right? And then this zeta, that's this guy, and there's 1 minus zeta p. That's this guy, right? So now I have some integral over c, and that's over the gamma j. So now I have these negatively oriented circles, right? So these are in D, right? But I'm integrating this sort of ugly expression over here. So that works, no matter where P is in gamma, right? So now let's suppose that P is in the outside of U, right? Then we're trying to get that the winding number is going to be 0, right? So let's give this a name. Call this H, right? And so we're really integrating H around each of these circles. Now this has 2 simple poles. It's very easy to see that they're simple poles. One is at this C1 over P, because then if I plug that in here, I get 1 over P, so that kills this term, right? And it's C is a biholomorphism, so this is definitely a simple pole, right? Another one is at Q equals 0, because that's where this guy is 0, right? So well, like Q equals 0, sorry, at Q1, which is 0, right? That's where this is this because that took 0 to 0, right? So the inverse also takes 0, 0. So that's another one. And again, that was a biholomorphism, right? So this is also a simple pole, right? So it has 2 simple poles, and this guy is never 0, right? Well, again, because it's a biholomorphism. All right, so let's figure out the residue. So we're going to use the residue theorem of H at 0, right? Well, so what you do here is at 0. So we're looking at the pole coming out from this term. So basically, we think of this function as this, because we can just put those in the numerator because they're not 0 at the origin, right? So they can be put in the denominator. I have a nice holomorphic function around 0. This guy is 0 around 0, so I leave that in the denominator. And this is a simple pole. So what we can do is we can just evaluate this fraction, this thing at 0, and the derivative of this at 0, right? And that's what happens here, right? That's what we're doing, right? We're doing this over this thing evaluated at 0, right? And if you look at it, it has to be minus 1, right? So because what was this was 0, so this is 1, right? Uh, you know, this is this thing and this thing cancel, right? This thing over here, and we have -1. Oh yeah, great. So -1. Now we look at the other pole, right? So the pole at phi of 1/p, right? So we do the same thing, except now, this thing is in the numerator and this thing is in the denominator. It's a little bit more complicated. When we differentiate, we're gonna get this minus sign comes out here, right? Otherwise, it's very similar, right? And we have this thing evaluated as that is 1/p, and we get, right? It's a little bit more complicated, but we have this -1 cancels this -1. Then we have this thing just becomes 1/p, and there's a p out here, and then this thing cancels this thing. 8. This is 1, right? So okay, so we have the residues are -1 and 1, and the point is that they have opposite opposite sign, right? And they're equal, right? Now, gamma 1 goes around 0, and some other gamma j will go around phi of c, of 1/p, right? Because r is large enough so that we go around everything, right? So that means well, some, maybe not some other, but some gamma j, right? Maybe even gamma 1, but it goes around everything in S, and that's in S, right? So we definitely go around both if P is in the complement, and therefore, when we apply the residue theorem, we just get 0, right? So that means that this thing, this expression over here is just 0, right? So gamma is homologous to 0 in U. Phew, right? So now let's suppose that P is in K, right? So we have P in K. That means that this guy, whenever I have when C is in D, right? I don't have that C inverse of C is 1/p, right? So maybe I could pull that back phi again, so it's not P, right? So because that was the complement, right? That after all these steps, right? Those are exactly the things that aren't in K, right? So that means that this thing only has one pole, right? So okay, so again we write that thing. Let me just put H in here, and that pole is 0, so I can just forget about all the other ones, just around gamma 1, right? And so it goes around the other direction, right? That's a key thing here. That's why I'm getting minus the residue, right? So that was, if we go back, right, if you look at it, it's the computation, sorry, pressing the wrong button. The computation is the same. It's this computation again, right? So, right, so it's, right, it's minus because we're going in the opposite direction, but it's the residue that was -1, so we get 1, right? And you can actually see that the winding number can be 0 or 1, right? That's basically, do you go around both points or not? All right, you always go around 0. All right, so let's use this lemma, right? So now we have the lemma is proved, right? So let's use this lemma. So this is the thing that we couldn't prove. I mean, we proved one direction of it, and we just used it, or you just used it, in one of those exercises. Well, in the exercise that was mentioned in the proof. But we want to prove that the complement of a domain in C infinity is connected if and only if U is simply connected, right? So you have a domain connected open set, and it's simply connected if and only if its complement in the Riemann sphere is connected. And forward direction is done. We've proved that was much easier. That if the complement is connected, then U is simply connected. So we have that. So let's prove the other direction. Suppose that this is disconnected, right? That means, well, suppose that there are two components of the complement, right? So there are some two closed sets, S and K. They're non-empty, they're disjoint, and they are, their union is the complement, right? So now, well, one of them has to contain infinity because U was a domain in C. U doesn't, doesn't contain infinity, so it has to be one of the, one of the components of the complement, right? These are maybe not components; these might be disconnected as well, but they are they are disjoint, right? So in one of these, infinity has to be in one of these, right? So let's suppose it's in S. So now let U be U union K, right? K is closed, right? S is closed. We can add one to U and we still get an open set, right? Because the other one is closed, right? So because S is closed, this guy is open. It's a subset of C because S contained infinity, right? So U prime cannot contain infinity, therefore it's a subset of the complex plane. And K is a compact subset. It's a compact, right? It's closed subset of the Riemann sphere. It's compact, right? And now it's a subset of U prime. So we have a compact subset of U prime. And so we apply the lemma to find a gamma, right? In U prime minus K, right? And such that it goes around, everything in K. It goes around K. In other words, gamma is not homologous to 0, right? That it should be, otherwise it should be 0, right? In U, sorry, right? So because these points in K are in the complement of U, right? So this gamma, which is in U, goes around something in the complement. Therefore, U is not simply connected. So we proved that if the complement is disconnected, U is not simply connected, which is the other direction, right? Or it's the contrapositive of the other direction. All right, so that's about it. Let's just think about an exercise using this. Just if you want to get another exercise in using the lemma. So suppose that you have a sequence of holomorphic functions, and this is a useful result sometimes. So suppose that you have a sequence of holomorphic functions on an open set that converge uniformly to some non-constant f, and everything is happening in some open set U, and let's K be a compact subset, right? Then suppose I take any neighborhood of K in U, right? We're going to call it V. So it's V is a subset of U. It's an open set, and it contains K, right? Now, the FNs are not eventually going to have the same number of zeros as as f on k, that doesn't work. I mean, the k can be sort of weird. It's like if the zeros move just a little bit, they might move off of k. I also could have this neighborhood could be very far away, so there could be some zeros coming out there that are not even close to k. But there exists some other neighborhood, so I can fatten up k a little bit, just a tiny bit, but still stay in V. So I'm gonna get some other neighborhood. Uh, Basically, I add myself a little bit of wiggle room, but not so much that I go outside of V, where V is an arbitrary one. So W is of course gonna depend on V. And then what you get is that then you have to have that f and fn for n large enough are going to have the same number of zeros in W, right? And because we're saying non-constant, it's going to be identically zero, right? So that's an application of dilemma, right? Basically, it's the zeros cannot move far from a compact set eventually, right? Well, cannot be too far in this, in this. If I go far enough in the sequence, they couldn't have sort of moved too far, right? If I, another way of thinking about it, I perturb f a little bit. The zeros stay near k, right? And I just, how much am I allowed to perturb? Well, that's these v and w, right? If I want them to be within v, really, well, there's some small w that's even smaller, right? And the zeros don't move, outside of the w, right? Okay, so that's an application. All right, so that's good for today. So next time we're gonna look at harmonic functions. So these are basically the real and imaginary parts of holomorphic functions. So that's what we're gonna do next time. All right, so see you then.